I think breaking a bond would require energy. So it can help that maybe forming a bond is easier. So we really have two questions. I'll tell you how I would look at it. I have two atoms and I want to make a bond, right? Do those two atoms need to make a bond? Not necessarily. They could just float off in eternity forever on their own. Okay? So why would they make a bond? So collisions, they just smash against each other. Why should they make a bond? Which side of the reaction do you think is more stable? Product side. Okay, so we could cheat on this. If the product side is more stable, what would that mean for our energy diagram? We'd have a reactant, we'd have a product with lower in energy, right? Did we require energy or did we release energy? Okay, how would we figure it out? The energy for the change of the reaction would be products minus reactants. If our product energy is lower in energy than our reactants, what's that going to be? It's going to be a positive value. It's going to take energy. It's going to... Products minus reactants. Sorry, I didn't do that math right in my head. If the product value is small and our reactant value is large, what's going to happen? It's going to release energy. Okay? Does it make sense to do that? Let's think of it this way. Does it make more sense to have atoms chilling on their own without making a bond or to make bonds? Which is observationally more common? Atoms by themselves? Is that a pure atom? Pure element? Am I a pure element? Is the pen a pure element? Your shoes, your clothes? Are atoms by themselves? There's very few atoms found by themselves. In fact, it's probably just the noble gases. Almost every other element is found with something else. Why? It is more stable. Okay? Which means when we're going through and looking at those systems, it makes sense to drop in energy to form our products, okay? To form a bond. Okay? It is more stable to have that connection than to not have that connection. And we have the physical evidence around us. Okay? Reactions don't go up in energy easily. We would have to push them to get energetic. Okay? Energies go to lower energy states. And if the lower energy state, as we see around us, is chemical bonds, the bonds must be lower in energy than our starting atoms. Kind of, sort of? What happens if you flip it? I now want to break a bond. Now we'd be going from our energy diagram, effectively from our product, up to our reactant. That's going to require energy to break that bond apart. Okay. So, what we're primarily concerned about in this unit, close out of that, is thermodynamics. So how do we predict and control whether a chemical reaction will happen? Okay? And this is an interesting question. Whether it happens, it says nothing about the speed of that chemical reaction. Okay? Because if we're going to talk about the speed of the chemical reaction, what are we concerned about? Kinetics. Okay? And in kinetics, that's going to be driven based off of what? Not the heat of the reaction. The heat of the reaction is our difference between reactants and products. That's the thermodynamics. What controls the speed of a chemical reaction? Our rate. Okay? Where's the rate defined in our energy diagram? Does this reaction happen fast or slow, going reactants to products? You don't? Okay, cool. We don't know. What information do you need to know how fast it goes? we would need to know that transition point. Okay? And so when we defined the difference between those two, reactant energy and our transition state, that's now our activation energy. That's the speed of our chemical reaction, or is dependent on our speed of our chemical reaction. If we switch this up and now look at this one, that reaction should be very, very slow. Why should that reaction be slow? The transition state is higher. There's a larger difference in energy. Okay? That becomes harder to clear that activation, and that reaction slows down. Which of these reactions can happen or will happen? The orange one or the red one? Both. Both will happen, okay, given enough time to make rate irrelevant. Okay? So when we're talking about thermodynamics, it's very much so just, does it transition? Does it happen naturally to go from reactant to product? Okay? That's what our concern is. Why do we care? Well, any of our life stuff that we'd want to deal with, how to make clothes, how to cool down our houses, deciding whether those things will happen becomes an important factor to help us control whether it's an easy thing for us to do or a really hard thing for us to do. Okay? So we want to take those considerations into play as we navigate this. Okay? So if we look at the energy and chemical reaction, we've got our atoms really far apart, which are higher in energy. As we bring them close to each other, it drops in energy, okay, and it becomes stable. That's the formation of a bond. That's lower in energy than where we were individually. We could theoretically continue to bring the atoms close to each other, but now the energy goes up. Why would the energy go up? Or we could even try, why would the energy go down? We look at atoms far apart. Why should it start to go down in energy?
Because they're not reacting with one another.
They're going down in energy. We're making a bond. By definition, that would be reacting. When we have atoms far apart, what's that orange part? Each of those atoms is represented by an orange circle. What is that orange circle? Weird question. What is it supposed to represent? Ooh, cool, the radius. I like that. Radius of what? The radius of what? An atom. What dictates the radius of the atom? Protons and neutrons. Where are the protons and neutrons found? In the nucleus. How big is the nucleus? Itty bitty. Okay? If that was the size of the atom, I probably can't even put a dot on the screen to represent the size of the nucleus. That's how small our nucleus is. So is the size of our atom, our radius, really being dictated based off of the protons and neutrons? No, it's probably the electrons. So why would we go down in energy? Okay, so let's do a dot to represent an electron. There's red on orange is probably a bad idea. Is blue better? I'll take that as a yes. Why should we go down in energy? What's that blue dot able to do when I now have a bond? Where should I draw the blue dot when they're bonded? Say again? Okay, can the blue dot be there? That would be the same space. Could it be over here? What can electrons do? Move, yes. Okay, so they can hop, skip. Someone said a really neat word, which we'll come back to in a second. Can I draw it there? How about there? How about there? Can I draw it anywhere in that space? Yes, okay. Can I draw it here? For the record, big arrow. That's where it now is. Am I allowed to draw the electron there? Some people are like, yeah, okay, why? Why can I draw it there? It's bonded. What does bonded mean? Sharing what? You're sharing electrons, which means the electrons can jump from one space to another space. Is that a good thing? Is that a lower energy state? Okay, what do we do to penalize people? Isolate them. We put them in a 10 by 10 box and we say, do better next time. Okay, what are we doing here? We're giving them more space and allowing those electrons to move. Is that going to be a good thing? Yeah, electrons are kind of like people in that respect. That's cool. We can drop in energy. We're now happy because the electron can move to more spaces. It can only do that because I made a bond. If I don't make a bond, can the electron hop? Nope. What happens as I continue to smash them to each other? Why should it now go up in energy? We just said the electron can hop. What now progressively gets closer and closer and closer? Say again. The nucleus. And what's the nucleus going to do? It's going to repel the other nucleus, which is why we start to spike up in energy. You've started to bring those positive charges near each other. Right? The nucleus is still down here. Why can the electron jump? What does it see on the other atom? The nucleus, which is why it's now able to jump to interact with that positive nucleus. That's creating that sharing. As we continue to go closer and closer, we start to force those nuclei closer and closer to each other. And that causes a repulsion. That repulsion we see as a spike in the energy. Okay? So it can go all the way back to, I would argue, kind of Lewis structures. How do we draw these things and what do those things represent? Kind of, sort of? Okay. And of course, if we can go through and now define these bond energies, what are we going to then want to do? As we do with all things in science, we want to actually quantify it. So we'll go ahead and put together numbers to represent the energy stored within each of those individual bonds. Why would we expect it to change? Why would it not be constant? They're all making a bond. Isn't the bond the same? Aren't all bonds drawn with a line between them?
Yeah, but some bonds have
Keep going. Some bonds have.
double bonds, triple bonds.
These are all single bonds, though. All this, well, except for the bottom. Ignore the bottom. Okay. All those single bonds all have different values.
Yeah, they have different sizes too.
Okay? We could talk about the radius. What are you ultimately talking about? It's the strength of the attraction between electrons on one atom and protons on the other. It's how those things are tied to each other. And because we're changing the identity of the elements in each of those cases, what's going to happen to the nuclei? It's going to change. What's going to happen to the energy of the electrons? They're going to change. Which means what's going to happen to the strength of the attraction between them? It's going to change. And so we could now go through and quantify each of those systems. And so what we end up talking about is something known as bond energy. It is really easy to get lost within bond energy because you'll always see it as a positive value. Okay, but how are we going to use bond energy? Well, we may want to break the bond, or we may want to form the bond. How does that change our bond energy? If I make the bond, how much energy do I need to put in? I'm going to have to put in a positive value. So if I want to make the bond between two hydrogen atoms, I have to put energy in so that it can drop 436 kilojoules. Am I actually putting energy in when I make that bond? Did it require energy to make the bond or break the bond? To break it. Which means if I'm starting with the individual atoms and I put them together to make that bond, did it require energy? No, I lost energy. How much energy did I lose? 436. So I could say I lost 436, or I can say, what's our mathematical symbol for loss? Negative. And so what's going to end up popping up constantly throughout this section is the meaning on the sign negative. Okay? And in particular, is it accounted for in the term that you're using to define that situation? Right? In which case it's implied. If I lose energy, I can say it was negative 436. Okay? But is that a negative times a negative? Yeah, so I have to be real careful with the terminology that we're using to ensure that we don't have double negatives pop up. Kind of, sort of? Okay. The heat released or absorbed is called the enthalpy change. Should that be familiar? I'm hoping that is. That should have been 151. Okay. So you talked some about enthalpy changes, and we can look at positives and negatives. Those positives and negatives that you had to worry about when you talked about enthalpy are going to come back again, because we're still going to talk about enthalpy. Exothermic, you're releasing that heat. That would be a negative delta H. Okay? Looking at our energy diagram, our products are lower in energy than our reactants. Okay? We don't see negative energies because we're talking about potential energy. The only place we see negative energies is when we talk about a change. And that change is signified through the delta symbol. Endothermic reactions, our energy is absorbed. Okay? It requires energy to cause that system to go through and happen. So based on the bond energies, would you predict this reaction to be endothermic or exothermic? Which is energetically stable, which is more energetically stable, i.e. lower potential energy, reactants or products? This is another blue box, which means we can start to talk about it at your individual tables. Okay? We talked through the general statements, but now you've actually got to start quantifying and putting those numbers to work.
Bond energy between the bromine is less than the bond energy between the chlorine.
How'd you figure it out? What is our mathematical system that would allow us to get to this? We could take our product energy. Wait, product minus reactant? We're taking our reactant energy minus our product. What's our product energy? Let's try that then. Our product energy is 328. Why'd you say 328?
Oh, wait, you switched it. Oh, no, I didn't. Product energy.
Just asking. So now I'm hearing a 276. This is an interesting dilemma. That's why I'm asking.
Oh,
So
it really is because
you are intuitively saying that it's exothermic, which is great. Okay? So if it's 276, if it's exothermic, 276 minus 328 would get us our negative value, right? And if we did the other one, it would get us a positive value. So what I asked for was the how. Okay, and the first statement we got was product minus reactant. Which one matches? Is 328 our product? I mean, that's the CCl. Isn't that on the product side? Okay, you're saying no, so why?
It should be reactant minus.
Okay, so again, why? So we know this is our answer. How are you getting to this? Okay, so we're saying bonds broken. Now what? Minus bonds. Does that align? Does that match what you intuitively came up with? How easy was it for you to have that formula memorized?
Second nature.
Okay, you're being sarcastic, right? Just checking on that. Right? That becomes an interesting dilemma within this. You have to have that frame of context to be able to nail these things down. Okay? So if we're evaluating this formula and you're struggling with that, what might be a good thing to go through and do? Write it down. Where should you write it down? I love that. It's a good idea.
Paper.
What paper?
That's paper.
Note paper. I would argue no. Note paper isn't good enough. What was that?
Your cheat sheet.
You're allowed a cheat sheet on the exam, right? If you know that you're struggling with this, it's not blanket notes, right? Or maybe that's what you were calling your, yeah. Put it on something that you need for the exam. So that quiz. Does that make sense? This is a formula that you needed to be able to solve this. You struggled to remember it. Don't worry about remembering it as long as you've identified that that's going to go on your cheat sheet. Make sense? Okay. Next one. Why is the carbon-chlorine bond stronger than the carbon-bromine bond? Why would we expect the carbon-chlorine bond to be stronger? Right? Well, if we're going to figure out this ranking system of stronger versus weaker, there must be something different inherently about that carbon-chlorine than there is about that carbon-bromine. We go, oh, well, it's the numbers. The numbers are just saying which one's stronger or weaker. The question that was asked is why. So what is the inherent difference between chlorine and bromine?
Radius size.
The size of the radius. Okay? Bromine is significantly larger, which means what happens to the length of that bond? It gets longer. Okay? It starts to approximate not having a bond. That's effectively a weaker bond. Okay? Or you spin it and look the other direction. Chlorine being smaller is bringing those two atoms closer to each other, okay? Making it look less and less like individual atoms. That's now a stronger bond. So you can use those physical observations of size to help you come up with predictions on why you would expect one versus the other. Kind of neat. Good observation that you made really, really, really fast. All right. Energy and chemical reactions. You've got our exothermic, stronger bonds in products. Did we just talk about this? Okay. Or endothermic, stronger bonds in your reactants. Okay. So if you have a visual representation of this, you can do the intuitive jump. That's not the right button. You can do the intuitive jump that at least several of your classmates went through and did here, or you have to go through and do the formula system to ensure that you have those calculations done correctly so that you can draw those conclusions. Does that make sense? Right. Calculating our enthalpy change, right, to go through and look at bond energies. The example that we just looked at was relatively simple, right, or straightforward. We had those numbers already calculated for us or determined for us. Right. What we'll end up encountering is something known as the enthalpy change of formation. Okay? What does it mean for the enthalpy change of formation? What do you think? If I want the enthalpy change of formation for water, is water the reactant or the product?
Product.
How do you know it's the product?
Because you have two different molecules bonded to each other.
No. It's on the right side of the arrow only because she said it was the product. So just to be obnoxious, now I'll put it on the left side of the arrow. Why should the arrow be placed where it's supposed to be placed? What about the term enthalpy of formation gives you a clue as to where that species is located? It's forming it. Okay? So use the language to help you identify where it's located. And great intuition on where it was located. We just needed a little bit of push to get those words down. Okay? The enthalpy of formation suggests that what we're doing is making that material, okay, and we're making it from the elemental species. Oh, that's probably why I picked water, because it was written right there. I was trying to pick something else. Okay? You'll note an interesting thing pops up. Or maybe we'll try it this way. What do you note that's interesting about this equation? Let's get rid of that EX. And maybe it's not interesting to you, but I know it would be interesting to Chem 130 students.
The half information.
Cool. Is that interesting to you? Are you used to seeing fractional values showing up in a balanced chemical equation? Okay, no. Okay, so it is interesting. Cool. Why? Why is it there?
Because you want 1/2 of that O2.
Okay. We want 1/2 of the O2. Why? Why can't I just go through and put a 2 here, and make that a 1? So as a half, you're right, it does balance the equation. But why aren't we showing it 2, 1, 2, which is what we would typically do when we looked at balanced chemical equations? Why are we now saying we have to bring in this half? It is on the slide. By definition, when we talk about enthalpy of formation, it is to make 1 mole of your compound. That is it. Which means we can do whatever we want now as far as balancing to ensure that we get just that 1 mole. So you now have the potential to see fractional values show up as coefficients. Okay? We're now changing our dynamic of how we're evaluating. Why might we want to do that? Right? Because it'll simplify the output of our data. When we look at the heats of formation, it's now always by definition 1 mole of that species. I don't have to get fancy and say, well, no, it's 2 moles for water because there were 2 in the balanced chemical equation. Okay? So it simplifies our data output and our data collection system if we define it as 1 mole. Okay? The next little piece that we can draw attention to is there's this silly little circle thing. That circle thing means standard state. Okay? Standard state, which I think is interesting, is being stated at 25 degrees Celsius, 1 atmosphere pressure, or 1 molar concentration. Okay? Why or 1 molar? If I looked at gases, what unit would I use?
Atmosphere.
Atmospheres. If I looked at solutions, what unit would I use? Molar. Okay? So we're changing that unit system depending on what phase system we're working with. Okay? Why is calling this standard state interesting? Have you heard standard state before? Maybe STP? Yeah, what was STP? Standard, there's that standard word, temperature and pressure, right? So standard temperature. What was ST for standard temperature and pressure? You all remember? It's kind of a vaguely appropriate answer, if that helps as a hint. 0 degrees Celsius. That's standard temperature when we talk about gases. Why is this weird? It's at 25 degrees Celsius, and yet what are we calling it? Standard. There is no standard, unfortunately. It's the standard adopted for whatever that system is. Okay? So please be careful with that and pay attention that you don't lose track of that. Typically, it's not going to matter because if we're going to try and use these standard enthalpy formations, we have to ensure that we're at those conditions. Because if we're not at those conditions, does the tables of stuff that we look up hold true? No, they're all invalid. Right? So more often than not, your standard state is going to be held constant. right? And we get yet another formula that we could go through and do, okay? If, again, you struggle with formulas, that's okay. Write it down on your cheat sheet so you now know that you can constantly make reference to that. Okay? I will fully admit I struggled to hell with this area of content. There were so many negative signs and positive signs and calculations from one place to another that I always lost track of what you were subtracting from what. Okay? So I switched it around in my own head to stop looking at the formula and start thinking about what it meant. If I'm talking about a chemical reaction, A plus B goes to AB. Okay, or actually, let's make it goofy. And I want to figure out the enthalpies, a standard enthalpy for this chemical reaction. I would look up the formations, the heat of formations for each of these substances. I'd look up A, B, and CD. The formation for CD, where is CD going to show up in my heat of formation? Left side of the arrow or right side of the arrow? The right-hand side, where does it show up in my equation? On the right-hand side, which means don't touch the sign. It's already where it needs to be. If I look up the enthalpy of formation for A, in the enthalpy of formation, where is A? Left side of the arrow or right side of the arrow? If I look up the enthalpy of formation, what does formation by definition mean? I'm creating something. So if I look up the enthalpy of formation, the delta H I'm going to get shows that A on the product side. Where do I want my A? On the reactant side. So what do I need to do to my delta H? Flip the sign to get it to appear on the correct side of the equation. You mean following the formula. Okay? That minus sign within the formula has an intent to align your individual species so that they show up on the correct side of the individual equation. But what you're doing is Hess's law, right? You did Hess's law 151? You're effectively doing Hess's law. You're just changing where your energy term appears in your chemical equation. Kind of, sort of? And if you don't like that approach, that's okay. You got a cheat sheet. Write it down. Make sense? Put it to work. Calculate the enthalpy change for the combustion reaction of butane. We want to know, is it exothermic or endothermic? Which is more energetically stable, reactants or products? Start processing. Okay, remember, there's a couple approaches to how to go through and solve this based off of walking around. The common number popping up is negative 5,271. Okay. I think I heard a 0.4 being associated with that. Okay. How do you go through and do this? You've got that formula, you just plug it in. Okay. I'm not going to backtrack to that formula quite yet. Okay. Longhand version of what I would go through and do, I would write down each of my equations. Okay, I know those are formations, so the formation is C4H10. How many of them? 1, because it is 1. Okay, do I need, not 4, 2, right? Do I need 2? Yeah. How do I account for that? I account for that at the end, effectively Hess's law. I need that equation to run twice, so there's the 2. Okay, not only do I need it to run twice, do I want this to be a reactant or a product? Reactant. So what do I do? There's the sign change. Right? Oxygen. Formation for oxygen is going to be 0. Because when we're talking about the formation, it's the formation of that species in its elemental state, which is oxygen gas. What are we working with? Oxygen gas. It's already in its elemental state. Okay? And when we talk about the heat of formation in the elemental state, that's kind of the definition. It's going to be 0. Okay, so I don't have to contribute that one. I look at CO2. right? Formation again, carbon plus oxygen, CO2. My number was 393. I'm placing it on the right-hand side. Why am I placing it on the right-hand side? I know it was a negative value here. That negative says it was released. So when I talk about the formation, that's a negative value. Place it on the product side. Okay? I want to multiply by 8. Why do I want to multiply by 8? I have 8 CO2s. Do I want to change the sign? Nope, because it's already on the product sign in my final equation. Okay? Move through with the water. Same process. Water heats of formation. Formation is 241.8. Again, I'm writing it on the product side. Why? That's what that negative sign means for me. Okay, how many times do I want to run it? I want to do it 10 times. I can run my calculations, add up those numbers, okay, and then see what that sign is. If the sign that I'm spitting out of that calculation is negative, what does that mean? It's on the wrong side of the equation. I would need to flip it to the other side. Okay? Does this process work? It has worked for me always. Okay? And that's the fun part. It always works for me. You know what didn't always work for me? The formula that most of you should have gone through and used. Okay? That formula, come on, close that. Right there. That's what that formula gives you. That formula comes from understanding what's happening with the individual reactions. Okay? So you can choose to trust someone telling you that this formula has a basis, a scientific basis, or you can choose to not trust people. Man, that comes out not so great for me. Not trust people and solve the whole system of equations in and on their own. How do you decide which is more valuable? Okay. I think I heard you mouth test it. Okay. You could test it, practice. Okay. I would argue it's going to come down to consistency. Are you consistently right? With whatever method you're using, that's the method you should stick with. Does that make sense? Got another one. This one has you draw an energy diagram. The other one probably did too. Now that you trust the formula, hopefully, or you see that my process was a painfully long process, you should be able to go through and do our formula calculation. Set it up again. Once you've got an answer, draw an energy diagram. How do we go through and use the formula? So the last one I went through and wrote it all out was effectively a Hess's Law question. Okay. Well, we've got our formula written up top. We got the E, the goofy E, meaning sum. So what I want to do is, for me personally, I would run that first term. Okay. I want the number of times, that's my N, that my heat of formation of that material showed up in my equation. Okay. Since I'm looking at products, I'm going to start with the calcium oxide. The calcium oxide showed up negative 635.1. All I'm doing is reporting it directly into it. What's the coefficient from my balanced chemical equation? 1, so I can drop that in. It's a sum, so I'm going to add. Now, again, the next species of my product, CO2. CO2 formation was negative 393.5. Coefficient for my balanced equation is 1. Now I want to subtract. Okay? Again, I don't trust myself with formulas. I set this up with 2 separate systems. Okay? I would then go through and do the reactants, same process. Look at the reactants, calcium carbonate. My number is negative 1206.9. How many times does it show up in my equation? Once. I would run the calculation in blue, run the calculation in orange, and then run the subtraction. If we run that subtraction, we should be getting a number 178.3 kilojoules. Okay? A question popped up with, well, when do you need 1 mole of thing? The 1 mole of thing is coming from where? The definition of the heat of formation. That's where the 1 mole comes from. Okay? That is the definition of your heat of formation, which is why when we use this formula, what do we have to also incorporate? Our N, the number of times that thing appeared in the chemical equation. That's why we're using that N, because our heats of formation are by definition 1 mole of that material. Kind of, sort of? Do you feel a little better? Okay. How do we turn this into an energy diagram? Oops, wrong eraser. Don't all tell me at once.
Ask again.
How do we turn it into an energy diagram? First and foremost, I need some axes. What do I want on the x-axis? Our reaction coordinate, which is our reactant progressing towards our product. What do I want on the other axis? What is that?
Potential energy.
Okay, our potential energy, call it PE. That's what I've been noticing Dr. Steinman I just call it E, but that's fine. Okay, that's our potential energy. We now need to draw on our diagram what we know about this. Well, what do we know about it? How do we know it's endothermic? This symbol was positive. Okay? This is where you could include a parenthetical if you really wanted to in that plus sign to add extra emphasis to the state, whether it was endo or exothermic. Positive would be endo, negative would be exo. If it's endothermic, what does that mean?
It's absorbing energy.
It's absorbing energy. What does that mean?
Its products would be higher than the potential energy.
Products need to be higher than our reactants. Based off of this information, can I draw in this curve?
Not yet.
You said, not yet. I just did, though. Why am I not allowed to do it?
Because you need your transition state.
Okay, that's my transition state.
Activation energy.
Okay, and you're right. You're absolutely right. I'm just kind of devil's advocate here. We would need to know the activation energy, to know the height of that transition state. When we talk about the thermodynamics, we know none of that. All we know is the relative position of our products to our reactants. That's it. If I want to find out more information about what's happening, okay, with that transition state and that activation energy, I have to go back to the last unit and maybe retake the quiz. Ta-da. Too soon? Make sense? The next fun part is enthalpy doesn't tell the whole story. So in theory, all this enthalpy conversation should be reviewed mostly from 151. Okay? And what we discover is that there's another aspect to our energy that isn't quite addressed for or addressed. Okay? Because what we're trying to think about is what happens when we look at reactants to products. If I've got a bunch of gas particles, okay, in a box, if they don't make and break any bonds, could the energy of the system potentially change? Okay? If I add energy in, what could all those particles potentially do?
React.
No chemical reactions. I could sort them. I could have one particle set go to one side of the box and another particle set go to the other. That requires me putting energy into the system, and yet I made and broke no single bond. If I look at the difference in reactant energy versus product energy, they're exactly the same, and well, they aren't necessarily exactly the same. The organization has changed, and that's going to change the overall energy in the system. Because if I now put all those gas particles up on the side, held energy there, and I let go, what are the particles going to do? They're going to start to move and diffuse through each other. Again, no chemical bonds are being broken or formed, and yet there's a natural flow of energy. So there's something missing from our discussion on our energy system. It's not just the bond energy. There has to be a new concept. Okay? You do not have to trust me on this because I'm not 100% positive, but the scientists that went through and talked about this or first looked at and described this provided the name entropy to this concept. Why did they pick the name entropy? Enthalpy had already been defined. Everybody saw enthalpy as this really big, important concept, but nobody was addressing this new concept of the organization, the natural flow of how things move without looking at bond energies. And so allegedly what they went through and did is said that this concept that has yet to be defined is so of critical importance that I want to name it as close as possible to enthalpy so people recognize its value.
That's a good idea.
Welcome to now being a student on the flip end of that, and it's real easy to get those two terms confused. Okay? That was the intent, allegedly. Okay? Entropy is this concept of how things move. They're possible states. Those possible states, and technically microstates, aren't physical states, but what we're talking about is kind of how those things can exist and where they exist when they exist. Okay? We've got a little cartoon. I don't have Instagram, and apparently Instagram locks me out of things unless I sign into it, so we're not going to click that link, but you guys can click it. Because I've tried to look at some videos and it just yells at me. So you could go through and watch that video. What this is, the comic is potentially looking at, is talking about the disorder, or the randomization of things within someone's room. You have to put energy in to maintain a clean room. If you don't, what's going to eventually happen is everything kind of scatters off into the wilderness. Okay? That has been used to describe entropy, a measure of disorder. Okay? I would argue it's less disorder and it's more about possibilities. Okay? So if we look at a different system, okay, the box on the left, okay, made up of two boxes. So there are two possible states for this single box, or for the single blue atom. It could be in the left box or it can be in the right box. So when we're describing what's happening within our entire system here, there's really only two options: blue left or blue right. What happens when I move to the right box? Now how many options are there? Well, there's blue left, blue right. There's yellow left, yellow right. Red left, red right. Green, orange, pink, on all of those possible states. And those potential states can interact together. So we could look at the system where they're all in the left-hand side of the box, or they're all in the right-hand box, or they're different amounts in each of those individual boxes. All of those are possible states to describe what's happening within that system. Okay? Kind of, sort of. That's what's represented by entropy. Okay? And you'll hear this word microstates come out of that. Okay? What we're just trying to describe is the different ways that these things can exist. Okay? So entropy of a system increases as the number of ways the matter and energy can be distributed in that system. Okay? Or as that system, or those, what the words say. Okay? So what we're looking at is how the entropy can change, either go up or down. Okay? So take a look at these systems. Whoop, before we do that, go ahead.
I just want to say, can you post the slides? Because they're not.
I'll try and post the slides. Dr. Schnebel may be actually posting them right now. I honestly don't know. We start at 8:30, so 9:45, right? Okay. Determine which substance in each pair has a greater entropy. Okay, and explain your choice. Sit at your tables, talk at your tables, figure it out. So we'll go through kind of my choice for this. So entropy, again, I think is a challenging concept to deal with or to represent. Full disclosure, this was by far my worst lecture ever, was dealing with entropy. Massive, horrendous failure. Okay, so I've been a little panicked about having to give this class today. Hooray. Because the only way that I got better with it is that, number one, I failed miserably at the lecture and was like, I know how to do it, I can tell you all the answers, but I have no idea how I got there or why I got there. And one of the spins, and for the record, it wasn't just like showing up in class and just doing it. I looked at 4 different lecture sets of slides, talked to 5 different faculty, and none of them gave anything that seemed to be cogent enough for me to grab a hold of to actually tell students. Okay? So what I went back to is re-looked at everything and just said, well, none of it makes sense. I'm not going to look at any of it, and I'm going to recreate my own system. Okay? And it worked. The next lecture, I would argue, was like hands down one of the best lectures I've ever given. Right? And one of the big flips that kind of helped me a lot was not looking at entropy as the standard definition, which is, the amount of disorder, or microstates. Because what the hell is a microstate? That doesn't really make any sense either. Look at it as a form of motion. The more motion, the more entropy. Okay? So if your particles can move more, they're going to have naturally more entropy. Okay? And you can repackage that back to disorder. It still does the same thing. You can package it back to microstates. But it's really just an increase in the amount of motion of your particles. So if we start with the first one, liquid to a gas, which one has more motion? The gas. Okay? As the physical state, the gas can occupy your entire volume, whereas the liquid can only occupy the bottom volume, okay, if we're on planet Earth. Okay? So our possible microstates, where I can exist, which box am I in? I can get all of them with the gas. I can't do that with the liquid. If we look at the next one, fluorine at 50 degrees Celsius versus at 100 degrees Celsius. Which one has more motion? 100 degrees Celsius. That allows me to occupy a larger space, potentially. Okay? Ultimately, it can mean if I don't change the volume, my particles are going to move faster. They're now in more different microstates at any given second. Okay? The last one, 2 moles of oxygen gas versus 3 moles. Well, dang, they're both gases. Okay? Same temperature, presumably, because we didn't define it. Well, now we're out of luck. I can't figure it out. Well, again, which one has the potential for more things moving?
The more moles.
More moles. Okay? There was a small request to go back, so we'll look at that. So we'll put that back up real quickly for that definition. The ways your matter and energy, or what I'm effectively saying, is motion. Does it increase at the same rate? No. Where do you see sudden jumps? At the phase change, because it's now not just the particles moving more, but now you're actually changing that phase. And so one of the biggest ones is looking at that liquid to gas transition. That's a pretty huge jump. Why is the solid, where the hell is that line? Why is the solid to gas transition not as dramatic? That's not solid to gas. Thank you. Why is the solid to liquid not as dramatic as the liquid to gas? Because that's a huge jump from liquid to gas. Why is solid to liquid not as big of a deal?
Still remain like a similar volume, just increasing temperature.
Consider where the particles are limited to. Okay? Solid to liquid, there isn't much change in the overall density of the substance. There is some, okay? But that change is relatively minimal. You go from liquid to gas, you're exploding effectively the volume that your particles can occupy. So we would expect a much larger transition when we're looking at that liquid to gas as opposed to the solid to liquid. Getting a little grumpy because I'm not getting quite as far as I wanted. Okay. What would we predict? So we got a lot of things going on here. Should the entropy increase or decrease in each reaction? So which phase did we say was the most important? The gas phase had the most particle motion. So if we take a look at this first one, we're taking a liquid with a gas to produce gases. Let's just look at the reactant side. On the reactant side, which substance do you think is going to contribute the most to our entropy? The gas, which means to a first approximation, what can we do? Ignore the liquid. We can now move to the product side. What do we have? Two gases. Okay, two gases versus one gas. We should see an entropy change, right? We have different amounts of those individual particles. The entropy should be increased on our product side. What else did you notice changed? The number of moles of those particles. I'm going from 13 to 18. 18 is more particles. Okay? Not just more different particles, but more particles in general. That would suggest our entropy should go up significantly. How about the next one? Okay. So on the reactant side, we just have the solid. Okay, not a big deal. But we've got it. So it has some entropy. We can look to the product side. We have two phases. We have a solid and a gas. Which one's going to be the more dominant? The gas. So again, first approximation, I can ignore that. Okay. Now I'm going to compare across the equation because I'm looking at a change for the course of the reaction. Right? I'm going to compare my gas to my solid. First approximation. Where do I have entropy? Where I have something versus nothing. Something is more relevant. I have a larger entropy on the product side. I would expect my entropy to increase. Kind of, sort of. Entropy changes will be calculated just the same as enthalpy changes. Wait, I thought it was this slide. Okay. To the quiz, it says the answer key is posted. I don't know if she's changing. Did she post answer keys last semester for the thing? Okay. I must say it's a bad idea to look at the answer key right out of the gate. Okay. Just like I said, posting it last time is a bad idea too. What you should be trying to do is figure out what you did well, what you got wrong, and work through it. I do have cryptic handwriting, at least so I've been told. So if you have questions about anything I've written, please let me know. I tried to write the same thing, so it should be consistent kind of across the board within that. Okay? I do have office hours right after class. I'm more than happy to talk through it. Okay? Before you get an attempt to redo it, you have to submit this is what I'm going to change about that process into Canvas. I don't know if that assignment's there. I've got to look for that. It's not there. Okay. I will find where that assignment is, and I will get that one. Right? If you didn't get your quiz back, talk to me. I just didn't get to you yet. No sign-in sheet. I'll do it off of this.
Would you give her one?
So your base 3 is changed. That's good. Now let's look at what did you compare?
What is the value of grade? Oh, I'm so sorry. That's so horrible. Let's read the
Triple BH3. Did it change because I'm triple BO2? So when you're making this comparison, only your target.
Yours is awful.
And do it. You can solve it. You have to include
Like clown too.
for that tripling.
That's crazy. You told me like who read this second
So if you wanted to do that, you would have to solve this one first and then
Yeah,
solve
like bro definitely like jumped that more.
That's why I was like.
I didn't think you took that. I'm gonna ask him about it.